Okay, so what we're going to look at now is electromagnetic induction, okay, which is a method of generating electricity. Okay, you may be already aware that a generator in a power station comprises of spinning magnets. We'll have a look at spin later on. What we should have already investigated is the idea that there is this thing called magnetic field strength or magnetic flux density, and that is represented by the letter B as a symbol. Okay, so here we've got the magnetic field lines moving from north to south. Okay, if there is a higher magnetic flux density, we could expect to see more field lines to represent that higher density. Okay, hence the term magnetic flux density. That's measured in Tesla, and that's a capital T. Okay, using Fleming's left-hand rule, if we were to fire an electron into a magnetic field that is going into the board, the electron would follow that path. Okay, and it would go around in a circular motion. Okay, now, flux, magnetic flux, dropping the word density, just that word on its own, flux, is magnetic field passing through an area. So it's specifically the magnetic field over a certain area. Okay, so flux on its own is the magnetic flux density times by the area, where this is measured in Teslas and this is measured in meter squared. Okay, flux, we use the Greek symbol phi. You will have seen that before when you investigate the work function as part of quantum phenomena, and it's measured in Weber's WB, or just pronounce it Weber's, as most British people do, but it's after the German scientist Weber, so it's Weber's, that's WB. Right, now these concepts are important for when we're talking about electromagnetic induction. So that's inducing a potential difference across a wire. So let's have a look at this over here. So here I've got a wire, okay, it's not part of a complete circuit. However, we know that metals have delocalized electrons contained within them. If I was to grab this wire and I was to sweep it over an area of flux, okay, then what would happen is the motor effect would occur inside the wire. So even though it's not free moving in terms of it's restricted in a wire, the electrons will still exhibit the motor effect, and all of these electrons will follow that path when I move the wire over. Because of this, we'll have an area of negative charge where the electrons have moved to, and because the area will be vacated, that it will be less negative, you'll have an area of positive charge. Now if you think about the positive and negative terminals of a cell, here we've got an area of positive and an area of negative, therefore a potential difference occurs. So this is how it works. So this is how a dynamo on a bike would work, or anything that uses magnets to generate electricity. The wire cuts through the magnetic field line. Okay, so it's moving perpendicular to the magnetic field, wire cuts through the magnetic field line. A potential difference is induced across the ends of the wire. Okay, and because of this, current would flow if it's part of a complete circuit, and that's a 3-mark response. Okay, it's strongest when it's perpendicular, it is 0, okay, if it moves parallel. Naturally, we could move the magnetic field over the wire as well and get the same effect because of the Fleming's left-hand rule, they are still perpendicular to each other. So, if I was to move a magnet into a coil of wire in that fashion, okay, then it would give me a negative current. Okay, so if this moves in, then we get negative current. When we pull it back out, okay, then it would go to positive current there, and we'd get an alternating current going backwards and forwards if we were to repeatedly move that in and out. If the magnet is stationary, then it will return to 0, and that's because nothing is cutting through, cutting being the verb. When it's stationary, the current will move back to 0 on the needle. Thank you very much.